Hello, everyone. My name is Levi Starrett. I'm so excited to be here as part of this virtual conference. Today, I will be talking about model-based model compiling and its place in model compiler development. Before I get started, I'd like to quickly introduce myself. As I said, my name is Levi Starrett. I've been a part of the xtUML community for a very long time. I've spent 3.5 years as part of the OneFact Bridgepoint team. And for the last 1.5 years, I've been working for a company called Rogo, doing autonomous soil collection for fertility management in row crop agriculture. Currently, we are in the middle of our fall harvest season. Last fall, we sampled 80,000 acres of land in the Midwest, mostly in Indiana, Ohio, and Illinois. And this fall, we are sampling 250,000 acres across 8 states in the Midwest. I also love to spend time with my family. I have a picture of them up here, my beautiful wife, Courtney, and our 3 kiddos. First of all, I would like to lay some groundwork for model-based model compilation. What is a model-based model compiler? It is a program, which is an OOA model, that loads an OOA model into an OOA meta model and transforms that loaded model into an OOA of target. It then walks this model to render code into the target architecture. Let's break that down a little bit further. Before I continue, I want to introduce a project that I've been working on for several years called Ciera. Ciera is itself a model-based model compiler that generates generic Java. It's totally self-compiled. It actually builds itself with itself, and it's based on model-driven design. I've left a link here to the project page for those of you who'd like to go check out the project. We actually published the first public release of it in January of this year. It's an open source project, so it's free to use and contribute to, and we would love to see you over on that page. I will be using Ciera and referencing it throughout the rest of this presentation as a case study for model-driven development in model compiler design. So let's break it down. The elements of a model-based model compiler. First, we have to have an OOA of OOA. For Ciera, this is the xtUML meta model. Then we have to have an OOA of our target architecture. Again, in Ciera, this is an xtUML model that represents a Java architecture for a model compiler. This could also include a separate model for the target language. For example, Ciera could have a model of the architecture, which includes some of the design decisions of the model compiler and the architecture itself, as well as a model of Java itself. Ciera does not take this route. It has a more blended architecture model that has elements of Java, but also a higher level concepts such as transition table or component and things like that. Third, we have model transformations. These are rules captured in a modeling language to transform from one source model to a target model. This is the core of the logic of a model-based model compiler, taking one model and manipulating it to form another. Finally, there's the Schleyer-Meller runtime. This is the part of the model compiler. You could say it's the other half of the logical completeness of the model compiler that captures the rule of how things are executed in the model environment. This includes rules for dispatching events, timing rules, ports and messaging, and things like the base of the class model. There are also some required supporting tools to build a model-based model compiler. At very least, you need some way to load your instances into memory, into the model of your source. And in some implementations, you need a templating engine to be able to efficiently generate files and output models or output source code from the target model. Let's first talk about the OOA of OOA. In Ciera, this is the xtUML meta model. For this example, I've pulled up a couple screen captures from that model. This first one is the model of subsystem in the xtUML meta model. You can see we have model class and attribute, imported class, etc. And we also have another image here of the state machine model. These models will be loaded by the instance loader from the collected source model of the application. So in Ciera's case, we use the PyXTML pre-builder tool from the PyXTML project to gather all of the XTML models together into one cleaned up file and use an SQL loader to load those instances into memory. The next part is the OOA of target. For Ciera, this is in the form of several modeled subsystems, including the state transition table here and statement. So this is a model of OAL statement. And this model is designed and built around how the generated code will look and feel. The next step is model-to-model transformations. As I mentioned before, this makes up at least half of the core logic of the model compiler. These transformations are responsible for selecting into the source model and creating instances of the target model. Sometimes multi-pass transformations are necessary. For example, Ciera generates classes on the first pass of the model compilation, and then after the first pass creates relationships for each of these classes. It does this to assure that all classes have been created before relationships are created and linked up. There can also be additional post-processing steps, including linking up base types, post-processing types, or optimizing things. For Ciera, there's a feature that allows you to remove certain elements and prune the model after the fact if elements are not referenced through the action language. We'll talk more about post-processing later. Next is the Schleiermacher runtime. This is the part that actually enforces the rules of the method. It handles the event dispatch, and it defines the backend data management. It provides additional utilities like time and string processing and math and things like that. There are three basic approaches that I've observed in building a Schleiermacher runtime. The first is generating the runtime alongside the model every time you generate code for an application model. The second approach is a handwritten library that can be included dynamically with a model that has been generated separately. This is the method that Ciera takes. Another and newer, more experimental approach is to actually model the runtime and generate it from an xtUML model. Again, we'll talk about this a little bit later. First, let's talk about generating the Schleiermacher runtime from templates for each model. The example here that I'm going to use is the C compiler MC3020 that is included with Bridgepoint. One of the benefits of this is that it produces standalone code. Each generation of an application produces a single lump of code that can be compiled and run independently from any other dependency. It's also optimized specifically for the application. For example, the MC3020 model compiler only allocates memory for the number of events needed in the application. This saves space when you're compiling for a very small target. One of the drawbacks of this approach, however, is that it needs to be generated every time. And furthermore, it cannot be reused for generating modules that can be distributed. The second approach, that's a handwritten runtime, this is what Ciera does. One of the benefits of this is that you do not need to generate it each time. you can independently compile and package it and distribute it along with the model compiler. And each model that's generated can then just reference the runtime. This introduces the possibility to dynamically combine independently generated applications or domains. For example, you could build and compile a single xtUML domain and include the runtime and combine with other xtUML domains that use the same interfaces. One of the drawbacks of this is that it has a larger size because you have to include the entire runtime in any application. Another drawback is that it's maintained as handwritten code, where most of the other parts of Ciera are maintained as an xtUML model. A third option that I mentioned is a Schleiermacher runtime that is modeled. An example of this is MC Arch. Some of the benefits of this are all of the benefits of modeling an application model. After all, the Schleiermacher runtime is just a stateful system, so why not model it? Ciera actually did a presentation on this last year at Models Conference, or excuse me, at the xtUML Days Conference, and I've included a screenshot here of his model of architecture. One of the drawbacks of this approach, however, is the potential to lose target-specific optimizations. So a lot of times when you are building a model compiler architecture, you are attempting to build something that is very specialized for your purpose, and it can be difficult to do this with a generic model compiler architecture. Model compiler chaining. So I mentioned that we would talk about post-processing later. Something really interesting that you can do with model-based model compilers is model compiler chaining. So here in this graphic, I've shown how you can have multiple model compilers that operate on an instance population. So over here on the left, OOA instances from a meta model come into a core model compiler. The model compiler then generates code down at the bottom and outputs the OOA instances that were originally loaded into it, as well as instances of the target model. Additional model compilers can then load both of these sets of instances and perform additional operation steps on them and produce more code or modify existing code. This is actually how this is how Ciera works today. There's a core model compiler that generates all of the Schleiermacher application code, and then there's an additional model compiler that loads the instances and generates scaffolding for instance loading and dumping. And there's a third model compiler that loads instances of RSL templates into the model and allows them to be generated. So for every time the every time the Ciera model compiler is compiled, it is run through 3 separate and distinct model compilers, and their additional source output is combined to produce the model compilers. The OOA of Mazel is a very interesting piece of this puzzle. I mentioned that Ciera uses the xtUML meta model as its source model. This is not the only option for a source model. There's been recent work done to produce an OOA of Mazel through the Stratus project. I've included a link here, and when these slides are publicly available, you can follow that link to watch this video. It's about half an hour, but gives a really good detailed description and demo of the Stratus project. That project was commissioned to create a model similar to the xtUML meta model, but for the modeling language Mazel. This is based on an existing Java model from an existing Mazel C++ model compiler. The Stratus project provides full parse and load from textual Mazel into this source model, and a proof of concept transform renderer has been implemented as a model-based model compiler. This project is just ripe to build model-based model compilers for Mazel. The only thing that is missing is target-specific models and transformation functions. This is a huge opportunity for those who want to get into model-based model compiling. Let's talk about some of the benefits and drawbacks of model-based model compilers. One of the benefits is the clarity and maintainability. As I said before, a model compiler is just an application model, a specialized one that does a specialized task, but it can be modeled just like any other application. Performance is another benefit. So Ciera generates the GPS watch model in less than 2 seconds, not including instance loading. And this is seriously a huge improvement over the interpreted RSL model compilers, which struggle with large instance populations. Additionally, it's flexible. As with Ciera, you can build as many different model compilers as you want and chain them together to produce different types of code and different mechanisms in your application model, your output source code. And also, unlike the scripted model compilers where it becomes very, very difficult to distinguish between the query and the template, and it becomes messy and hard as you add features, model-based model compilers allow you to separate things with mechanisms like subtypes, generalizations, so that you can enable and disable different features without the model becoming spaghetti code. Some of the drawbacks, because there are drawbacks, is that at least in model-based model compilers that we've built today, OAL, or the action language itself, has some shortcomings. It can be clunky and not as expressive as we would hope to encode all of this logic in textual OAL. Additionally, the cost of setup for a model compiler is much higher than an interpreted model compiler. If you want to build a model compiler that just does partial generation, you could do so in about 5 minutes with xtUML, RSL, and an RSL template. However, with a model-based model compiler, it takes a little bit more project setup and a few additional supporting tools like that instance loading and templating. There are several existing examples of model-based model compilers. We've been talking a lot about Ciera. Escher, which is the modeled and compiled portion of the MC3020 model compiler, is an example. MCMC greatly increases performance of MC3020 by generating the action language portion. DocGen is another model compiler that loads an instance population and produces a model of document and then walks that document to produce an XML docbook spec. The xtUML to Mazel parser exporter is another example of a model, and it's actually an example of a chained model to model-based model compiler, where in one step, xtUML metamodel instances are converted to a serialized Mazel form, which is then loaded into a target architecture model from the Mazel textual language and then rendered to Mazel. And this is used by the Mazel community to export from xtUML bridgepoint models to textual Mazel and then downstream to their model compilers. Overall, the model-based model compiler idea is one that should not be surprising to us. A model compiler is just another application, and so we can use and leverage some of the real benefits of modeling in being able to visualize and talk about models and discuss them and verify them before we generate our application. Thank you so much for allowing me to speak. I'd love to answer all your questions. Thank you.